In this unit, we are going to be studying acids and bases and using the knowledge that we acquired from the equilibrium unit to better understand what happens during an acid-base reaction. But in order to study acids and bases in more detail, we need a fundamental understanding of what exactly acids and bases are. So the most fundamental definition of an acid or a base that you should be familiar with is the Arrhenius definition of an acid and a base. So an Arrhenius acid is actually one that increases the concentration of hydrogen ions when it's dissolved in water. So the traditional HCl, HBr, you have a hydrogen that's going to be produced when you dissolve it into solution. An Arrhenius base is a substance that increases the concentration of hydroxide ions when it's dissolved in water. What you should notice, though, is this definition limits you to aqueous solution. So you have to have hydroxide produced by the base and hydrogen ions produced by the acid, which limits you, as you'll see in a little bit. What I want you to do right now is I want you to use your textbook in order to complete the table that I provided, identifying specific characteristics of acids and bases. So pause this video right now, and then we'll continue on. All right, the next definition of acids and bases is a little bit more inclusive, and that's the Bronsted-Lowry definition. A Bronsted-Lowry acid is defined as a substance that donates a proton, while a Bronsted-Lowry base is one that accepts a proton. And so the acronym that I use to remember that is BAD. Bases accept, acids donate, BAAD. So let's look at some examples to see how these Bronsted-Lowry acids and Bronsted-Lowry bases actually work in a reaction. So if you look here, I give you a reaction. Hydrochloric acid is reacting with hydroxide ions to produce water and Cl. So the first thing that we need to do is identify the Bronsted-Lowry acid and the Bronsted-Lowry base. If you notice HCl, if you compare HCl to the chloride ion on the product side, HCl has lost that proton, the hydrogen ion. Therefore, it is going to be the Bronsted-Lowry acid. Hydroxide has accepted that proton, that hydrogen ion. Therefore, OH is your base. Keep in mind, I'm going to be using the term proton synonymously with the term hydrogen ion, because remember, if you have a hydrogen ion, the only thing that's left is a single proton. Now, there are two new terms that I need to introduce, and it's the concept of conjugate acids and conjugate bases. So every acid has a conjugate base, and every base has a conjugate acid. So for hydrochloric acid, because it's an acid, it functions as a Bronsted-Lowry acid. That means that Cl minus, the chloride ion, is its conjugate base, while for hydroxide, water is its conjugate acid. So water is the conjugate acid in this case, and chloride is the conjugate base. What you should notice is that up until this point, we've only been talking about one acid and one base. In order to have an acid, you need to have a base. However, if you notice, you now have two different acids and you have two different bases, because conjugate acids are still acids and conjugate bases are still bases. And so that begs the question, well, which side of the equilibrium is going to be favored? Meaning, will HCl and hydroxide function as the acids and bases producing more water and chloride ion, or will water and chloride ion be the predominant acid and base producing more HCl and OH minus, meaning where exactly does the equilibrium lie? And so that's a question we're going to learn how to answer right now. Before we can do that, though, we need to talk about strengths of acids and strengths of bases. Now, the stronger an acid is, the weaker its conjugate bases. So, for example, if you look at the top, hydrochloric acid is one of your strong acids. Notice its conjugate base, chloride, is weak to the point at which it has negligible basicity. We basically don't even consider it to be a base. And the stronger a base, the weaker its conjugate acid. So notice, for example, if you look at the very bottom, you have CH3 negative. That is an extremely strong base. Its conjugate acid has negligible acidity. So keep in mind, if you're looking at, let's say, for example, nitrate, the nitrate polyatomic ion, since HNO3 is one of your strong acids, when we're considering its basicity, it would be extremely weak. And this is going to play a huge role in being able to determine where exactly equilibrium lie in just 1 second. Now, just as review, in a previous unit, I talked about the list of strong acids and the list of strong bases. So let's make sure that we're clear on those. Here are your 7 strong acids. It includes hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. And then you also have your strong bases, any group 1 metal hydroxide, and then calcium, strontium, and barium metal hydroxide. So keep in mind, for all of these strong acids, they're conjugate bases, so the chloride ion, bromide ion, iodide ion, all of these conjugate bases are going to have negligible basicity. Same thing for the strong bases. Their conjugate acids are going to be so weak that we actually don't even consider them to be acids. So let's look at how this actually applies. So here you've got a reaction. You've got hydrochloric acid with water producing your hydronium ion plus Cl minus. So in this problem, just as review, you have HCl is your Bronsted-Lowry acid, water is your Bronsted-Lowry base, and I know that because hydrochloric acid donates its proton, therefore producing chloride ion, and then water accepts the proton, becoming the hydronium ion. Now, if I'm looking at this reaction, I know that hydrochloric acid is a strong acid, and looking at the chloride ion, I know that it's such a weak base I don't even consider it to be a base. Therefore, I know that water is a stronger base than the chloride ion. And therefore, this reaction, if you notice, you don't have the double arrow, because the reverse reaction actually isn't going to occur. Hydrochloric acid and water are strong enough bases that what's going to be produced is pretty much only hydronium and the chloride ion. The reverse reaction does not occur because the hydronium ion and the chloride ion are much weaker than hydrochloric acid and water. Now, if you look at this example, you do have the double arrow, so clearly we're going to have to compare the strength of these acids and bases. So if you look at the first acid, that is acetic acid. Acetic acid is a weak acid. Now, weak acids have weak conjugate bases. Now, that makes it seem like we should ignore it, but by a weak conjugate base, I am saying that we have to consider its basicity. And in fact, that's actually a stronger base than water is. Similarly, the hydronium ion is actually a stronger acid. Therefore, when I'm looking at this reaction, the equilibrium is actually going to lie on the left-hand side, meaning that I'm going to be producing more acetic acid and water. So just as a couple of rules to help you to figure out where the equilibrium lies, in every acid-base reaction, the position of the equilibrium is going to favor the transfer of the proton to the stronger base. So for example, here, for the second problem, for the second reaction, the equilibrium is going to lie on the left-hand side because the stronger base is actually the acetate ion when compared with water. Also, the position, just to further emphasize this, the position of the equilibrium favors the reaction of the stronger acid and the stronger base to form the weaker acid and the weaker base. So that means that the top reaction, hydrochloric acid and water, the position of the equilibrium favors the formation of hydronium and the chloride ion because those are the weaker acid and base. In contrast, since the hydronium ion and the acetate ion are stronger acids and bases, then the equilibrium is actually going to favor the formation of the acetic acid and water. So we're going to look briefly and review writing neutralization reactions. And then we'll move on to talking about hydrolysis reactions, which force us to come to terms with the fact that the salts that we produce in these neutralization reactions don't actually simply exist with water. They can actually exhibit acidic or basic properties. So we're going to look at that in just one second. Let's first review briefly the reaction for a strong acid and a strong base. So my example that I gave was hydrochloric acid and sodium hydroxide. When those two react together, you have the typical neutralization reaction of sodium chloride and water forming. Keep in mind that since hydrochloric acid is a strong acid and sodium hydroxide is a strong base and sodium chloride is soluble, what you're going to end up with is simply hydrogen plus hydroxide producing water because everything else is a spectator ion. Now, what if that's not actually the case? What if I have a strong acid and a weak base? So in this case, I have hydrochloric acid reacting with zinc hydroxide to produce zinc chloride and water. Now, hydrochloric acid is a strong acid, so it's a strong electrolyte, so it will dissociate into its ions, and zinc chloride is soluble, and so that'll produce, if you notice here, you've got your hydrogen ions and chloride ions breaking apart. Zinc hydroxide does not because it is not a strong electrolyte, and zinc chloride breaks apart, and then you've got water. So the net ionic equation for this neutralization reaction is what I just showed you right there. You've got hydrogen ions, you've got zinc hydroxide not having broken up, and then zinc ions and water. What about if I have a strong base and a weak acid? So sodium hydroxide reacting with hydrofluoric acid. There's your reaction right there. Keep in mind that sodium hydroxide is a strong electrolyte and sodium fluoride is soluble. Therefore, you're going to end up with this. If you cross out your spectator ions, this is going to be your net ionic equation. So let's now look at hydrolysis reactions. So now we're going to actually work with writing hydrolysis reactions in order to predict whether a salt is an acid or a base. So keep in mind, for hydrolysis, this is actually a reaction that's occurring. This is not just dissolving a salt in water. So to start off, I have to show the dissolving of potassium fluoride. And so potassium fluoride, when it dissolves into potassium ions and fluoride ions. Now, we have to think about where these ions came from. So potassium is going to be the conjugate acid of potassium hydroxide, while the fluoride ion is going to be the conjugate base of hydrofluoric acid, of HF. Now, potassium hydroxide is a strong base, therefore the acidity of K+, that's insignificant. But for the fluoride ion, since it came from HF, which is a weak acid, I do have to consider the basicity of the fluoride ion. Therefore, if you look at this reaction here, this is the hydrolysis of the fluoride ion. Notice fluoride acts as the Bronsted-Lowry base when reacting with water, and it forms, therefore, hydrofluoric acid because it's a conjugate base. It's going to accept a proton, plus hydroxide because water acted as the Bronsted-Lowry acid to donate a proton. Do notice this brings up one really important fact, and it's the fact that water can either act as a Bronsted-Lowry acid or a Bronsted-Lowry base.